This is more important.
I mean, the easiest thing to do is let's say you have a so let's say you have a I can make a classical proof by like
Yeah, we just switched the adapter.
Yeah. I think I just need to program it within like because like as long as the distance from one state is like
So they would have to be filed.
So then I just need to track each individual curve.
Sorry.
Yeah. I don't think it's like I don't yeah, I like I would take out
This is both happening.
yeah, I got
So these are Robert, do you have it? Did it come up on your? Do you have it in your email? Do you have the topic? Sorry.
my full manager.
Okay. Various people. Wait, sorry. Oh.
Harvard.
I just had to.
Yes. Like, yeah. Yeah. So we go to MIT the next major. Yeah. Yes, we do that.
Sorry. No, no, of course. Yeah. It's called Pauli. Thanks.
Which is Jordan Cotler. He's going to tell us separations between learning and
Thank you so much for giving me the chance to speak. So in the first part of the talk, we've already seen results about the hardness of classical computation. But now that the talk is able to start, we'll talk about quantum computation. So this is work joint with Sitan Chen, Jerry Lee, and Robert Huang. Robert's right here, gave a talk a few talks ago. And the subject is exponential separations between learning with and without quantum memory. So let me begin by asking a question, namely, what is an experiment? Now, as scientists, we have a sense of what an experiment is intuitively. But if you think about the sheer variety of examples that fall under the purview of experimentation, it's actually not so obvious what an experiment is. So let me give a few examples of what we learn by doing experiments. So certain examples of what we can learn include measuring constants of nature, such as the speed of light or the charge of an electron, quantifying dynamical properties, such as the rate of a chemical reaction, or inferring structural properties like the symmetry group of a crystal, or maybe even learning more abstract information, such as the chain of chemical reactions that comprise photosynthesis, whether Yang-Mills describes the strong force. This emphasizes that we should ask, what exactly is an experiment in its full scope of generality? Now, there have been some interesting recent perspectives towards addressing this question. So one was in a paper by Huang and Prestel earlier last year, in which they stipulated that many experiments can be thought of as quantum learning algorithms, which learn properties of partially uncharacterized systems via examples. A related perspective from around the same time is that all experiments are examples of what are called quantum algorithmic measurements, or QALMs, which are a hybrid of black box algorithms and interactive protocols. And these works build off of previous works of interactive protocols. The idea is that by having a crisp understanding of what an experiment is, we can bring to bear the tools of computational complexity theory to analyze the resources that are required to perform experiments and to see which kinds of experiments are hard and which are easier given whatever resources we have at our disposal. So I'd like to draw out the distinction between what I'm going to refer to as conventional experiments versus quantum enhanced experiments. So let's first begin by defining what a conventional experiment is at an intuitive level. So suppose that we have three systems, subsystems. We have nature, which is the system that we wish to interrogate. We have the lab system, and we also have the classical memory, which we can think of as our classical computer, which stores and processes classical data. The nature, here is a picture of graphene, the system that we like to understand. The lab is our apparatus, which directly couples to the system. And our classical memory is, again, our classical computation that stores and processes classical information. Now, the workflow of a conventional experiment is that we use data that we have stored in the past on our classical computer upon which we have performed classical information processing. We use that to inform our apparatus what measurements it should make on the system in nature. The system in nature then responds and prints some result on the measurement apparatus, which we then decohere. We measure classical outputs we measure and store classical outputs which can be processed on our classical computer. Now, in this entire process, the information which is stored by our classical computer and which is communicated to the apparatus and then back to the computer itself was all classical in nature. But this information all here is all classical. In other words, we do not have the ability to store quantum information and do quantum data processing. Now, let me juxtapose this with a more interesting possibility, which I'll refer to as a quantum enhanced experiment. Here, we have similar setup. We have nature in the lab. But now, instead of having a classical memory, we have a quantum memory in a full-fledged quantum computer. So in this particular protocol, we can store and process quantum data. And we can use that quantum data to inform which measurements we should make on the experimental system. And in turn, when we receive data from the experimental system that we've measured, we're not forced to fully decohere it. Namely, we can store and process the quantum data that it provides and use that to inform future measurements that we may make in future experiments that we may do. So here, the information that is transferred between the systems is quantum, completely quantum. Now what we would like to do is to study the power of quantum enhancement. We're going to establish that there exist experiments with an exponential complexity separation between the conventional and quantum enhanced settings. That is, if you have a quantum computer in the lab, there are certain experiments that you can do exponentially more efficiently than if you only have the ability to do classical information processing. Now, there are two parts to this endeavor. On the one hand, we want to show that an experiment can be performed efficiently with a quantum computer in the quantum enhanced setting. But on the other hand, we need to show that that same experiment is exponentially hard in the conventional setting. Now, the first part of this is comparatively easy. We only need to exhibit one efficient quantum enhanced experiment that does the job. On the other hand, the second part is hard because we need to rule out the possibility of all efficient conventional experiments, even under the assumption that we can employ an adaptive strategy. So in a conventional experiment, you can use previous information that you have stored and measured to inform future measurements that you make. We would like to establish that even if you have the ability to do that, it still is not going to allow you the same advantages as a quantum computer in an exponentially emphatic way. So the contributions of our work is really mostly developing techniques for the second part of this, is that showing that an experiment is exponentially hard in the conventional setting. So there's been recent work in this direction on exponential separations in gate and query complexity for learning properties of classical orbitals. Now, the work that we're going to build off of here are these two papers that I discussed a bit earlier, a few slides ago. One in which is by Huang from Presco about exponential separations from query complexity for learning Pauli observables. And this other work that I mentioned, which talks about exponential separations in gate and query complexity for learning properties of quantum states and channels. So in our work, we synthesize and generalize the approaches of a work by Liebeck, Chen, and Li, this paper by Huang from Presco, and by Avronov, myself, and Shi. We provide a new framework, as I said, for proving exponential lower bounds for protocols with classical memories, which allows us to prove new exponential complexity separations between interactive protocols with and without quantum memory. So let me sketch the basic idea of the framework, which is called the learning tree framework, what we call the learning tree framework, in particular for learning states. So let's suppose, in a simple example, that we have the physical source which produces the density matrix rho. And we want to learn about it in the setting where we don't have a quantum memory, namely in the conventional experimental setting. So one way of conceptualizing this is that we query the source, we get a copy of rho, and then we measure it using a POVM, which in general we can refine into a rank 1 POVM. Let's not worry so much about that detail. And suppose that if we measure in this POVM, indexed by these BIs, that the output is Q, namely that we measure V sub Q. And we store it in the classical memory, namely the classical output Q. So then in the next round of the experiment, we again obtain a copy of rho, and we measure it using another rank 1 POVM. But in this case, the new rank 1 POVM can be contingent on the previous classical measurement outcome. That is, it's indexed by this Q, which we previously measured in the last round. Now suppose that the output is R, namely that we measure V sub QR. And we store that in the classical memory. Okay, so to illustrate one more time, in the next round, I'll say it a little bit quicker. We obtain a copy of rho, we measure using a rank 1 POVM. And the point is that it's V sub QRI. It depends on both previous measurement rounds. And suppose that the output of this is S, and we store that in the classical memory, and so on and so forth, etc. So how do we conceive of this? Well, one way of visualizing this is as a form of tree. In the first round, we obtain one of a number of potential POVM outcomes, say V2, and contingent on that outcome, we then measure another POVM, which is at another layer in the tree that is contingent on the previous measurement outcome. So we traverse our way as a root to the leaf path through the tree, and a particular instantiation of the protocol, a particular sequence of measurement outcomes is a path through the tree. Now, a tree of depth T, that is T rounds, corresponds to measuring T copies of the state. So to delve a little bit further, suppose V naught for Vt minus 1 are the locations of the vertices that they root to leaf path through the tree, designating a particular protocol. And the probability that we take that path is just the product over the rank 1 POVMs that are located at those vertices, sandwiched against the state rho. So this is the probability that we take a particular root to leaf path through the tree if we receive the state rho each time. By contrast, if you receive the state sigma each time, then this would be the probability over root to leaf path through the tree that we would receive. So what we're going to be interested in is bounding the total variation distance, essentially the one norm between these two distributions. If we can't tell, if we are either always given the state rho or always given the state sigma, and all protocols essentially look the same to us, we have the same rough probability distribution over outcomes of sequential outcomes through this measurement protocol, we can't tell this apart, then we can't tell apart rho and sigma at a reasonable number of measurements, namely of depth T measurements. So there's two basic strategies that we will employ. One that we call an edge-based strategy, in which we bound the information a learner can gain by traversing any edge through the tree, meaning the information you obtain by doing a single round of the protocol. Now, a different strategy is the path-based strategy, in which we bound the information gained for traversing an entire path through the tree. So let me now put this to work. Let's talk about exponential separations in learning quantum states. We'll start with some simple examples and work to some more complicated examples. First, let's consider purity testing. So results already from a year ago. So let me say the task and then the result and then the new result. The task is, suppose that I task you with distinguishing between, on the one hand, the maximally mixed state. Namely, I give you the maximally mixed state each time you ask me to give you a state. Or I always give you a fixed R random state each time you ask me to give you a state. And you want to know whether one possibility or the other possibility is being realized. So it turns out that the number of queries that you require to distinguish the two possibilities, if you have access to a quantum memory, is essentially order 1 queries. You can just do a swap test to determine whether you have a pure state or a mixed state. But if you only have access to a classical memory, it requires a lower bound of exponentially many measurements. And the proof of this classical lower bound in this paper with Aharonov and Shi is about 20 pages and rather technical. Now, in this new work, we were actually able to get the proof down to a half a page. And in fact, the result is tight. That now if you look at we see here there's a theta, that we have an asymptotically tight upper and lower bound of 2 to the n over 2 measurements, which are required in the classical setting for achieving this purity testing result. So now let me tell you about some other examples about Pauli state property testing. So suppose we're given a density matrix, identity plus p, where p is a Pauli on n qubits, over 2 to the n. So p is a Pauli string, and our goal is that we would like to determine p. Now the complexity, the query complexity of being able to do this in the setting where you have the quantum memory is efficient, but in the classical memory setting, it takes up to log factors, basically 2 to the n queries in order to achieve the task. Now a related protocol with quantum memory can actually be made gate efficient and was recently instantiated in an experiment in collaboration with Google, and various authors are in this audience. And this also resolves in various ways that I can talk about during the questions of conjecture, which was posed in this paper with Aharonov and Shi. So let's now, good. Now let me talk about a result of shadow tomography without a quantum memory. So given a state rho in a collection of observables O1 through OM, our goal is to determine the expectation values of all those observables to within epsilon error. Now a result from the present work is that the number of measurements which you require in the setting where you only have the classical memory in the conventional experiment is up to log factors. Is lower bounded by the minimum of n, the total number of observables, the minimum between m and 2 to the n divided by the error squared. So the upper bound is from the paper by Huang, and Prestel. We have supplied the lower bound, and this resolves, getting both the upper and lower bound together resolves an open problem from Aronson and also Aronson and Rothblum. Now let me tell you about exponential separations in learning quantum channels. We've talked about learning quantum states. Let's turn to the question of learning dynamics or learning channels. So in the first problem, which I'll call the fixed unitary problem, our goal is to distinguish between, on the one hand, giving you each time the maximally depolarizing channel, and on the other hand, giving you a fixed Har-random unitary. So I either give you one every single time you query a black box, or I give you the other, and your goal is to determine which of the two you're receiving. You're always going to receive the same oracle each time. So in the case that you have a quantum memory, you can do this with a small number of queries by, again, doing something like a swap test. But in the context where you only are able to do a conventional experiment, it is exponentially hard to distinguish between the two cases of being given a maximum depolarizing channel and being given a fixed Har-random unitary. Moreover, the protocol with quantum memory can be made gate efficient. And the results in this work with Chen, Huang, and Li actually generalizes in some very interesting ways the original results with Aharonov and Shi in 21. Improves the bound exponentially, in fact. Let me give you a problem that's maybe a bit more physically motivated. Suppose that we would like to learn the symmetry class of the dynamics of the system. So we'd like to distinguish between, on the one hand, being given a fixed Har-random unitary, or on the other hand, a fixed Har-random orthogonal matrix, or on the other hand, a fixed Har-random symplectic matrix. Now, these three different classes of unitaries realize three different forms of time reversal symmetry of unitary. The first kind doesn't have any time reversal symmetry, but the latter two instantiate different forms of time reversal symmetry. And if you're tasked with determining which of these three cases the oracle I provide you with falls into, then if you have a quantum memory, you can do it efficiently, essentially order one queries. But with a classical memory, it requires a lower bound, an exponential lower bound than n, to determine the difference between these symmetry classes. Now let me tell you about a qualitatively different kind of result, about exponential separations with bounded quantum memory. This is qualitatively different than the results I've told you about before. So before, we were comparing classical or conventional experiments with quantum enhanced experiments. But now we're going to do something different. We're going to talk about just the power of how, if you only have a quantum computer with a fixed number of qubits, what is the power that you have if you have less or more qubits? There are certain experiments that you can do if you have more qubits that you couldn't do if you had fewer qubits. So let me state the results and we can unpack it. Suppose that you have a quantum computer with n plus k qubits, and I give you copies of a state rho. And what I ask you to do is to prepare the or to determine for me the absolute value of the trace of a Pauli string against rho for all n-qubit Pauli strings. And I want you to do this with some constant probability. Interestingly enough, if you only have n plus k qubits, the number of copies of rho which are required to complete this task is exponential in the difference between n and k. So here's what this means. If you have 2 n qubits, you can do this task efficiently. But if you have less than 2 n qubits, if you only have n plus k qubits, where k is less than n, that the number of copies that you require is exponential in the difference between n and k. If you don't have enough memory, if you don't have enough space, it takes you an exponential amount of time, or it's exponentially many queries, I should say. So this combines the proof techniques of all of the results previously mentioned. And this is an exponential trade-off between quantum memory and query complexity. Let me conclude with one other set of results, about which under the name of replica quantum advantage. So suppose that we want to learn some property of a quantum state rho. Now we could ask the following question. Are there any circumstances for which this property is exponentially hard to learn if we only have access to k copies of rho at a time? So I give you k copies of rho at a time, you have to measure all of them, and only once you've measured all of them, I'll give you another k copies of rho. But the property is easy to learn if I give you suitably more than k copies of rho at a time. So in the case of k equals 1, the purity test that we described is an example of k-replica quantum advantage. So let me show it again. If I give you 1 copy of either a maximum mixed state or a fixed Haar random pure state at a time, it's very hard to determine whether, it's exponentially hard to determine, you require exponentially many measurements to determine whether it is a mixed state, or a maximum mixed state or a Haar random pure state. But if I give you 2 copies at a time, it's easy, you just do a swap test. So this is a difference between giving 1 replica at a time versus 2 replicas. What's interesting is that for k greater than 1, that we actually find that in a different paper, even though it's with all the same authors from the same year, we find that for every k greater than 1, there is an example of a k-replica quantum advantage. And if I give you k copies of rho at a time, there is, for a particular class of states, there is a property which is exponentially hard to learn. But if I give you access to suitably more than k copies of rho at a time, that property becomes extraordinarily easy to learn, at least in terms of query complexity. So this is some idea of quantum parallelism, that if you have the ability to do computation on k copies of your system in an interesting entangled way, this can confer a kind of exponential advantage for learning certain kinds of properties of the system. And moreover, this is not just the difference between 1 copy versus 2 copies, but there are more sophisticated properties of the state that you can learn, for which, if you have 5 copies, you can't learn it. If you have suitably more than 5 copies, you can learn it. So let's conclude with the discussion. So the usual paradigm of quantum advantage is that quantum computers are better than classical computers at performing classical problems. But what we're talking about here is a slightly different set of questions, which I'll call quantum learning advantage. Namely, the quantum learning has advantage over classical learning for performing quantum experiments. This is particularly relevant to understanding nature through quantum experiments, because nature, systems that we wish to interrogate in the lab, condensed matter systems, whatever, quantum chemistry systems, they are quantum systems. And we would like to learn classical outcomes. Only as humans, we read classical outputs, we read papers that say in classical text what the outcome of an experiment is, but we would like to manipulate a quantum system to get some desired classical output that gives us insight into the nature of the system. And that's the paradigm that we're discussing here, which is different than the ordinary circumstances of quantum advantage. So what have we done? We've developed a new framework for proving exponential separations between quantum learning algorithms with and without a quantum memory. In fact, some of these and versions of these results were actually recently demonstrated, as I mentioned, in collaboration with Google on their Cotler processor. We've also established the first exponential trade-off between bounded quantum memory and query complexity. I think that this is very exciting. It's interesting to see what is the power of a small quantum computer versus a larger quantum computer. These kinds of results allow us access to that kind of understanding. Another question, which Robert discussed a few talks earlier, what are the effects of noise? Having a better understanding of how robust these results are, or the ways in which they're modified in the presence of noise, is a very interesting open question. In fact, Robert alluded to in the end of his talk some results along these lines for similar tasks. But what I would like most is examples of other physical examples. It would be so wonderful to live in a world in which every experimentalist would want to have a quantum computer in their lab to interface with their experiments, to be able to learn something about their system of interest. And even though we're working with some toy examples here to prove these exponential separations, I have a hope that we can generalize this to experimental tasks that experimentalists would be very excited about. I don't know how to do that, but we'll hopefully there'll be a way to do so in the future. So with that, thank you so much for your attention.
Maybe I'll ask a question to okay.
Okay, so you had some very nice examples of cases where you have this very large separation between quantum and classical memory.
Yes.
Do you think there's any hope to say anything general about which sorts of problems we expect to see such separations and which not?
So we've thought about that a bit, and what's interesting is that there seem to be certain categories of problems which have different mechanisms by which you achieve the advantage. And we don't have a complete categorization or classification, but it's at the moment we're just trying to collect as much data as we can to figure it out. So at the moment, I think that there's maybe 3 or 4, depending on how you count it, different kind of mechanisms at play, which we've been able to leverage in different examples. But there's no reason to believe that this is exhaustive.
Hi, thanks for the great talk. So in your setup, you have what you call a quantum memory, which you want to store information, and you would use that to inform the next step of your experiment.
Yes.
Does that imply that your lab apparatus essentially needs to be able to process and compute the quantum information to be able to make an, let's say, an updated step, at which point is your lab apparatus in fact a quantum computer? And so it's not about quantum memory, but about having a quantum computer, or is there not much of a distinction between the two?
The way that I've been using it, having a quantum memory is essentially indistinguishable from having a quantum computer.
Okay.
You can do whatever processing you want. What we've emphasized in the results is how much memory is available to store. That's why it was convenient to call it quantum memory. But if you wish, you can think of it as a quantum computer with bounded size.
I see. And are there intuition about what it might take to, the computation you would need to turn the stored memory into something useful for your next experiment?
Yeah, so maybe what you're asking is a lot of the results I've told you about query complexity instead of gate complexity.
Right.
Now, some of the results, many of the results actually generalize to the setting of being efficient in terms of gate complexity, but there's a caveat, which is that, for example, in the purity testing example, when I say I either give you a Haar random pure state or a max and mixed state, well, how are you going to prepare Haar random? How is nature going to prepare for you a Haar random pure state? That's exponentially complex. So the thing that you really want is a problem for which there's an exponential separation jointly in query and gate complexity, and for which the state source channels that you're trying to distinguish between in nature are also, say, polynomially easy to prepare. And we actually do have an example of that, and that kind of thing is exactly the example that was done on the Google Sycamore process, because you can do it.
Great. Thank you very much.